Thank you very much, Alex. It's an honor and pleasure to be here. And so Alex asked me to try to bridge academia and industry. And I thought that one way to do this would be to talk about programming as programming to understand programming. So kind of in a more reflective way. And so this is why my title is Programming Should Eat Itself. And I want to start with this quote from SICP, which is the evaluator which determines the meaning of expressions in a programming language is just another program. So here you have this hint that, well, a program can have another program as data. And I wanted to take this further by referring to the literature on towers of interpreters and reflective towers of interpreters. So turtles all the way down. So at the top here where the elephants are, we have the user level. And then you can think of each turtle as a meta level. And just to make it, we can just represent it this way. So the user level is actually the meta level 0. And then we have the first meta level, the second meta level, the third meta level. And we can keep going down. So it seems like at some point we need to stop. And the question is, can we, once we take this idea and not try to be just meta-circular in the sense that the user level semantics and the meta level semantics are using the same language, but also be reflective in the sense that each level above, so for example, the meta level 0 is defined semantically by the meta level 1. And this one is defined by the meta level 2. So you can change each level independently. All right, so this is a bit abstract, and I guess it's time for some code. And for this demo, I will be using the reflective language Black, which is implemented in Scheme, and it's a code that's accompanying a paper by Kenichi Asai and others from 1996, and I will have references at the end. So let's see. All right. So here I have a normal Scheme prompt, and just for those who are not familiar with Scheme, basically you just this is just a shell, so I can evaluate one. And then the way it works is that when you have a parenthesis, the usual thing is that you have an application, and the first position is the procedure or function, and the other positions are the operand. So I can do this. I can also define functions. So let's say inc. And then just say this. And I can also just anonymously call functions and use them. All right, so this is pretty basic. Let's play with Black now. So I'm loading the Black system. And now I'm going to Black. And here we see that we've started at this new prompt, which says 0 and 1. So the second number is really just like the number for the current query. And the first one is at which level we're at. So now we're at the meta level 0, which is the user level. So like before, I can define inc. And then do inc2. But now let's say I do a typo. And now I've moved up to the meta level. So you see this one here. And here it's also a normal Scheme prompt, so I can do this. And now in order to go back to the lower level, I just use this continuation. And since the error happened when evaluating this increment function, we expect to have some value that would match here. So I can just use any function here. And so this will return 2. Because basically, it's kind of as if I had resumed computation here. And with this lambda x, x, I get 2. All right, so let's go to the meta level again by doing the error again. And now, another thing I can do here is I actually have access to a base evaluator. So base eval is a procedure here. And this is one way that I can, from the meta level, inspect what is going on at the user level. So I can say base eval, inc, and then I also have to provide some environment and some continuation, which I will explain. So before doing this example, let me just do a simpler one, where I can say base eval 1, for example, and use an empty environment, and just the identity continuation. So this returns 1 at this level. And now if I do this, I actually get the definition of inc as data from the lower level. So now I can again here jump to the lower level by doing alt-cont. OK. So this was equivalent to basically continuing with the inc function at the error here. All right, so now we've seen a little bit how to go one level up by triggering an error, but we can also just go up explicitly by using this exit, which kind of means like go down in this turtle chain. So if I do exit hello, I'm back to the first level with the value hello. And I can keep going up. And now I've loaded a new level, which is the meta level 2. And again, I can go down step by step. All right, and there's another thing we can do, which is go basically this em function, which is exec at meta level. But I'll just use em because it's easier. So I can say em1, for example, and this is executed at the meta level, but we stay at the level 0. So that's not so interesting, but I could do em, say, define foo equals 1. And now this foo is not defined at level 0, but now I've bumped up to level 1, and it's defined here. And so if I continue with this. All right, so that's the basic thing. And one thing that's interesting is with this em, we can also do that if we want. And that would be defined at the second level, but not, say, the first level, and things like this. All right, so now let's look at what we can do with the system. Just to first give an idea of what's going on, we have this base eval interpreter, which is kind of in this typical meta-circular style, except that it has a level of indirection to be able to build this tower. So one thing we can do is define, say, let's say we want to define a new yeah, so let's say we want to define just a simple instrumentation function. So it's actually a little bit the way this black system is set up. It's using mutation a lot, but the gist of the idea is that you can at the meta level. So let's go up. At this level, I can say, OK, define original eval application to be the eval application. And now I can modify it to do something else. So let's say I do set eval application so that when the first argument, yeah, so let me just write it somewhere so that it's easier. So I can do this, and each of these things, like the base eval, they all always take this expression, this environment, and this continuation. So here, for example, I can say when I have when my expression is So already we know it's an application, so we know it's a pair. And we can say when the first element of the expression, let's say, is my, then here I want to do something special, which is to be defined. And otherwise, I just want to call the original eval application with exp as before. So now I have to choose what to do here, and let's say I'm just returning my and ignoring all the arguments. So now I can define this at the meta level, and if I go back, and now let's make sure things are still working, so this should still work. But now if I do my2, I just get my back. Well, this is actually interesting, because let's say if I have a completely looping function, so let's say this is just calling itself, so that's an infinite loop. Oh, actually, I'm back. Yeah, so here I made a mistake. I just returned my instead of using the continuation, so I ended up on the wrong level. So what I actually wanted to do here was call the continuation to go back to the original level. So let's evaluate this again and go back. OK. All right, so that's fine. Now I'm back at the original level. And so now if I do this loop function, which I definitely don't want to call, and let me just, well, I guess I don't want to call it, but maybe I can, just for the fun. Yeah, so it's looping, and now I've messed up my buffer. But anyway, so yes, let's kill it. Restart. No. OK, so I'm back here, and now I'm actually going to load directly this. Let me put this in a file, like live black, for example. And I'm directly going to load this from the meta level. OK, so I can do this live black. All right, so now let's define this loop function again. Right. And now if I do my loop, that actually still works, because I've kind of added this my thing as a special form that when I'm doing the application, I'm not even looking at the argument here. I'm just looking at the first expression. So just for people who don't know scheme, basically this just returns the my, and that's all I'm testing. OK, so what interesting things we can do by changing the meta level? So one fun thing is instrumentation. And using the same pattern, I can kind of say, OK, well, if you have this instrumentation special form, then do this. And this is a function that I define normally. So the thing is, you can think of it as macros, but instead of macros being just these syntactic rewriting where you have to worry also about hygiene and variable naming, here we are just using a normal function at the meta level to do something special as like a macro. So just to illustrate this, yeah, just to illustrate this instrumentation function, I've defined these church numerals and things because, oops. Okay, this is getting strange. So, because I will actually go back to the strange loop. Yeah, I just loaded a strange version of that file, so it was completely messed up. Okay, so now if I load this file at level 0, I've basically defined all these data structures as number. So I guess some of you here might be familiar with, say, the church numerals, where you define a number by a function. Basically, you define the number n as something that takes a function and applies it n times to some argument, right? So 0 is just saying, well, we take this function and this argument and we just return it. And then 1 is saying we take this function and this argument and we apply it once, we can apply it 2, we can define successor, etc. So one thing that's been tricky historically was to define predecessor. And here I have kind of two versions of it, one which is using extra data structures like pairs, and another one which is a more direct version. And so I can try it out by doing, say, predecessor of C2. And then I'm converting it to a number so I can see it, and I get 1. Or I can do the alt version. Now, one thing we can do with the system is really just instrumentation as something that we've added at the meta level. So let me load at this meta level this instrumentation black. And now I have access to this instrumentation function, which takes any expression. And it calculates, say, the number of applications that happen to evaluate this. And here we have lots of applications because basically this encoding, the only thing you can do is create functions and apply them. And so we can compare the two versions and see that one has, this alternative version is much more efficient. And just to show how we can take this further, we can actually also decide to instrument everything. So I added instrumentation for app, lam, and var. So I can load this version. And now when I instrument this, I get all the information I wanted. Okay. Okay. Well, actually, so what's interesting here is that at the meta level, you can do what you want and treat it as data. So one thing that I thought was kind of cool is, let me actually rename this buffer to black so I can start a scheme buffer as well. And in scheme, I can define all right, so here I have some fancy function. And I'm not going to explain it in detail, but it's basically known as this Taba pattern, which is from Olivier Danvys and Al paper. And Taba stands for, I'll list the reference later. And Taba stands for there and back again. And so the idea is, let's say you you want to define, let's say you want to define this, actually the scheme has reverse, okay, good. Does it have zip? I guess it doesn't have zip. Yeah. So, okay, let's see if I have zip somewhere. Yeah. So the idea of this, one of the riddle, for example, is to say if you have zip of 1, 2, 3, and ABC. So you do that, and now the riddle is that you actually want to do this version with the reverse here, with n recursive calls. So it's kind of tricky to think about this, because in some sense, when you traverse this list, you want to do it one way, and then when you traverse this one, you want to do it the other way. So the Taba trick is actually quite clever, and I encourage you to think a little bit about how you would do it. But one thing you can do is this idea that when you're going down the stack, you're recursing on this list, and when you're going back up the stack, you're unwinding this list in the reverse order. So that seems very abstract, but in Scheme, if I define these traces here, let me just define this. Yeah. I can actually now use this version of convolution 3, 1, 2, 3. And here you see that I can see how it works. So the recursive calls are, I'm walking down the first list, and when I'm going back up, I have these two things here. So this first part and the second part, and I'm kind of building the result as I go back up by popping these things in the right way. The idea is because, yeah, you're kind of using the language stack to create this pattern. So I thought what would be interesting is to play a little bit in black and see if we can get a representation of this stack. And so let's see. So I've implemented several versions of it, and I guess let's look at the second one. So the idea here is that I'm also adding these things I'm adding this app hook like you've seen before, so that Taba is a special form. And then here, for every time for these calls that are like monitored by Taba, I'm actually adding things to build up the stack and create a data representation of the stack. So let's play with this a bit. Oops, okay, I needed to define. So see, now I've jumped like very high on the thing, but I guess it's going to be, yeah. So I'm back to 0, and I needed actually to import this utilities files. Okay, so now I have, let me load this Taba thing. And let me also load the stack, the stack here. Okay, so now what I can do is, well, and I should load the convolution file, but here I will remove the trace defines because, all right. So I'm loading this, and now I can use it this way by saying Taba, and I want to walk this and this, and then I can just call my function normally. So let's say 1, 2, 3. Okay. Whoops. Okay, it's loading in the other buffer. So let's see. Okay. All right, good. So now if I do this thing, I get this strange result out because I was getting the result and the stack, but let me say result and stack, and is this. And now the second argument should be the stack. And okay, it's hard to read this way, but this is really just some const cells, and I have this function to print it nicely. Right, so now I get this. Okay, I did a mistake. It's the car of this. Whoops. That's weird. Okay. Well, let me do this version, which I think is, because the stack was tested at the meta level, so there's some strange thing going on, but let me just do this version here with which would directly print the stack. All right, and now I can do okay. Yeah. So basically, I get this stack representation, and you can see here that, okay, you start this way, and you're walking down, and then, oops, you're going back up. And this was easy to print, because actually I had this, I created my structure, so I had this information at once, and this one at once, and this one at once. Okay, so how are we doing on time? Yeah, so 10 more minutes, so, well, or a bit more. Let's go back to the slides. All right, so I mean, I haven't answered fully why you would want to do this, and I'll get back to this. But first, also, why not? Yeah, okay. And then, so Dan Friedman, who has been working on this for many years, has kind of taken this exponential back-off approach to not working on it so much. And the reason is that it's made my head hurt. Yeah. And yeah, it's kind of like this cat chasing it, chasing its tail. And well, that's kind of what academics we do sometimes, right? We're like trying to understand some things in terms of itself, and we keep doing this. And I don't know, it's a bit strange, but it's also fun, and that's kind of what we do. So in terms of references, here are some of the papers where you can learn more about this. I thought this was something cool to show because, say, this is the paper actually from '96, which has the code. And then recently, Kenichi Aisai also had a paper in Gypsy where he uses meta-OCaml to do a sort of, also this kind of tower of interpreters. And the idea there is that with meta-OCaml, you can also compile some things so that you can specialize the code. So I thought to end off, I would just kind of sketch a little bit how this works from an implementation point of view. Actually, while I read Kenichi's paper, I actually went, and as I read through, I did an implementation of the paper. And to me, this is actually one of the most fun way to read a paper. Just go through it and implement it as you understand it. And the thing is, I actually tried to port this to Scheme, and it was really painful because I was getting these procedures, like these errors, and I really didn't know where things went wrong. And the reason is that actually the way this works is pretty complicated, and it helps to have a type system. So let me just show you the Scheme version, which doesn't work, just so you can get the idea of why it's hard. Let's see. So it's a really, oops, black. So I did a small black one, but I just had a hard time actually getting some things. But basically, you start with a base eval. And this is like just a normal interpreter, but you use these meta things to just be able to tie the loop in the tower if you want. And the thing that makes it complicated actually is that the way it works is that you can shift up and down the levels and you carry these meta continuation as well. And the thing that is complicated is that you have to know, okay, which kind of function I'm dealing with. Is it a primitive function? Is it a lifted function? And so on. But in the OCaml version, things become a bit clearer. Because what you see here is that the types help you out. So for example, this is, instead of representing things just as scheme lists, you actually have values that are typed. And you can say, okay, I either have a number, a symbol, or some sort of pair structure. And then I can have a primitive function, or just this representation for a user-defined function. Or I can have this eval function, which is actually the tricky one, right? Because this one is really tricky in Scheme because you kind of have these multiple parameters, and it's easy to mess one step. And to make it even more complicated, this meta continuation function is itself this, if you want, it's a sort of infinite stream of things. So the way to look at it is meta continuation is an infinite stream of pairs, it's an infinite stream of state. And each level has a state, so each state represents if you want, it represents the registers of a level. And so what you have here is, the way we're representing it is the first thing we have an environment, and then we have a current continuation. And then we have a stream of those. So it starts, this is like for level 1, and then another one for levels 2, etc. And we can keep going up as much as we want. But here, this is the end of the tail is lazy, so that we only build levels as we need them. And yeah, and this other stuff was mostly to play with compiling, but we don't need to understand it here. And so, okay, so now let me just give you an example of a function. So here's how you would define eval_var. And here you see in OCaml, I'm explicitly using this apply cont to apply a continuation, and it's a typed function. So if I look at apply cont, I can actually look at its type, I think. Okay, yeah, so actually here you see that this one is quite general because it's shifting up. But in general, I've put the thing. So let's just look at a more interesting example. So when I'm evaluating a list, what I need to do is actually, let's say I have a list of expressions. Yeah, like. Right? And to evaluate this list, what I need to do is actually, say, call the base evaluator on, if it's nil, then I just return nil. Otherwise, I call the base evaluator, and I recursively evaluate the list. And what's tricky here is that I have to actually lift those continuations as well. And so this is the part where in Scheme, I completely lost track of where I needed to do the lifting or not. But fortunately, in OCaml, it's easier thanks to the type system. All right. So, yep. Okay, so I think it's kind of a bit early, but I'm happy to open it for questions here and also requests for things you'd like to see. So. Any questions? Yes. Add types to your object language. Yeah, that makes sense. Yeah. So yeah, one thing I didn't get into at all is also the kind of the third part of the duality, if you want. So here we were talking about yeah. So basically we were talking about like program as data, data as program, and we can also kind of also add types and proofs maybe, right? And this would be, I mean, maybe not in the system, but actually even the title of the talk, Programming Should Eat Itself, was inspired by work in type theory. There is a type theory should eat itself, and like homotopy type theory, etc., should also eat itself. And the idea is, well, can you kind of define the types? Can you use your theory to define your theory within it, and how far can you go with this? So it's kind of a dual aspect. But yes, I think in terms of debugging, adding types to the object language would also be helpful. And like another thing I want to explore is with this new paper, the Gypsy paper. When it's actually using MetaOCaml, which is a generative programming framework, so that even though you have a tower, you can collapse some user function to low-level efficient code. But when you're doing this collapsing, you are also losing the semantics of the tower. And so one thing I would like to explore is maybe using the generative framework in Scala, which is type-driven. Maybe we can do this sort of interpreter to compiler transformation automatically, and then also collapse the tower with the semantics. And so just a shout out to Tia Krumpf, who's presenting some work related to this generative programming in Scala this afternoon. Any other questions?
Can you compare this sort of meta-level approach to f-expression?
Yes, so that's a good question. And I think in some sense with this system, you could implement f-expressions within it. And I think for the black system as it's defined here, it's kind of hard coding all these things, but you could imagine just having one more layer of indirection so that f-expressions could be easy to implement. But I mean, just to actually, I started doing that. So the idea is that, so here I had to do a lot of code because the system was not really, the base system was not really done so that it would be easy to add. But the idea is that when you add this special form, which is f expression, and you could use it as a lambda, right? So you do f expression x, let's say f expression y x, and that's kind of like lambda x, except that here you have to explicitly evaluate the argument. So here, if I wanted to evaluate x, I would need to do something like meta level x, right? And so I would need to add this special form for f expression, and then which is kind of what I was doing here. I'm just adding this this expression tag like we did before. But then the other thing I need to do is actually change the apply function when you evaluate an f expression, so that it so that when you see this as a value instead of lambda xy x, so the way it would represent this in the system is, in addition here you would have an environment, and here I would have the same. So I would also have some environment here. And then I need to change the application so that it doesn't eagerly evaluate all the arguments. So the idea here is that when I'm doing the application, I can actually say, well, just evaluate it without pre-evaluating the argument. So just to make it clear, if you have lambda x plus x1 and foo bar, like in scheme, what will happen is that you can think of it as evaluating this, and evaluating this, and then this, and then basically, well, actually, you don't need the foo here. And let's say foo is defined to be 2, then the result of this evaluation is some sort of closure, right? Closure representing plus x1, and foo is just 2, and this is where you have the application part. So app. Now for f expressions, what you do instead is that you would say, you would basically say, if I did fx plus 1, let's say. If I did this, I would just want to apply it as a fx closure if you want, and have 1 here, and not even evaluate the 2. So I would just be passing it. This as a symbol, instead of as the result of evaluation. And actually, another nice paper is by it's this one, Open Extensible Composition Modules, which shows that just by having a layer of indirection, let me make this. So just by having a level of indirection here, I can write my eval and apply in such a generic way that f expression would fall true. I think historically what happened was that f expression, where it was decided that they were it cost too much of a penalty for performance, because you would basically never know when you're able to optimize the arguments or not, because you wouldn't know whether they get evaluated. The problem is, if you look at here, it's like you have something here, and then arg1, arg2, arg3. Well, until you've evaluated this and understood whether it's an f expression or a regular lambda, you don't really know whether you can optimize the evaluation of these arguments. All right, any other questions? Yes, I think that's also a better idea. Well, one thing that I found difficult in this black system, it's that basically you're mutating everything on the fly, and so I mean, at some point when you get into a weird state, you just have to restart, and it's not clear. But I think that by refining the store, you could play some really cool tricks with just basically being able to undo as many times as you want and things like this. So I haven't played with that so far yet. Yeah. But I mean, I guess my hope with this talk is just to also get people interested in playing with these things for fun, and also as a way to kind of get some of the ideas from academia, like just playing with some of the ideas from academia. And so the way I usually do, and really the most fun I've had with papers, is really using this approach where I start with the paper and go really concrete and try to just play with the system, and then also do my own extensions. All right, so any other questions? All right, oh yeah? So it's, how is it different from scope? So scope in which sense? In the like, do you mean just like lexical scoping, or like actually dynamic scoping, or? Okay, yeah. So either. Okay. Yeah. So well, let's see. I mean the. So in some sense, what you can do is when you're adding these things at the meta level, you can also really scope things lexically, right? And you can also use like dynamic scope as well. But I think what you're saying is, how is this different from, say, just redefining? Say, instead of adding this at the meta level, I could have used trace define and get the same effect, right? Yeah. So yeah, I mean, I think in terms of practical application, I think it doesn't make sense to use this. It's more, it makes more sense as a kind of just this way of like, well, instead of programming to ship something, it's more about programming to understand the context of programming, understand like how you can express things. And the fact that you have all these levels is kind of a bit, it's actually, I'm still trying to think about other things we could do. So of course, talking with William Bird, we were saying, okay, what could you do if you had like a logic language at the meta level, right? So then you can have some sort of meta logic for your user level and things like this. So to me, it's, I see what you mean in saying that, okay, you can solve some of these, the same problem, the same issues, say with tracing and things without using this, this meta level approach, but this is more about, yeah, about kind of going back to the picture, like just defining your semantics in terms of another semantics that is similar. All right, anything else? All right, thank you very much.